The concept of stability of equilibrium can be understood by means of this very simple example. Consider beads sliding on a smooth wire. Let the shape of the wire be given by the function f of x, as shown here, with the bead sliding on it. Here we mean by smooth, we mean that there are no kinks in the wire. The shape of the wire is differentiable many times with respect to x, and there is no friction. What are the positions along the wire where the bead could be in equilibrium? Just thinking about it intuitively, we can imagine that the bead could be in equilibrium in one of these three positions, x1, x2, and x3. Which of these equilibrium positions is stable, we think? Just based on intuition, we would think that the positions x1 and x3 are stable, and the position x2 is unstable. So by means of intuition, what do we really mean by stability? We understand intuitively that if the bead is disturbed from a stable equilibrium point, then it stays close to the point. So if it's disturbed from x1, then it would stay close to x1. Whereas if it's disturbed from x2, then it would wander far away from x2. So we've kind of talked about this intuitively, but let's look at it more systematically. We'll consider the free body diagram of the bead when it was in this position x. So the free body diagram has the normal force and the gravitational force. Let the slope of the angle made by the tangent be theta. So if we do the sum of the forces in the normal direction, we get n minus mg cosine theta equals 0, and summing the forces in the tangential direction gives us mg sine theta equals 0. Now, just from geometry, tangent theta is nothing but f prime of x. So just from geometry, we can figure out that sine of theta is f prime of x divided by square root of 1 plus f prime of x squared. So the equilibrium equation mg sine theta equals 0 means mg times this expression for sine theta is 0, which means mg times f prime of x is 0. Now let's look at the potential energy of the bead. Since gravity is acting downward, the height of the bead is simply f of x. So the potential energy is mg times f of x. So we realize from this that equilibrium can be obtained by simply taking the derivative of the energy. Now let x star be an equilibrium point. So x star could be x1, x2, or x3. Now let's look at the second derivative of v. If the second derivative of v is greater than 0, as is the case for the points x1 and x3, then the equilibrium point is stable. If the second derivative is negative, as is the case for x star equals x2, then the equilibrium point is unstable. If the second derivative is equal to 0, then this information is not enough to determine stability. We will not encounter this very commonly, and we'll need to look at higher derivatives. We call this a neutrally stable situation. It's not something that we'll encounter commonly. We'll look at mostly v prime greater than v double prime greater than 0 or v double prime less than 0. So we see from this that both equilibrium and stability of equilibrium can be deduced from the energy of the system. Equilibrium is related to the first derivative of the energy and stability to the second derivative. These are concepts that we will carry forward to other more complex examples.